For centuries, every comet and asteroid humanity studied shared one basic trait. They were gravitationally bound to our sunday. They followed predictable, closed loops, staying entirely within our cosmic neighborhood. Then, in October 2017, the Haleakala Observatory in Hawaii detected a rock that broke that pattern. Dubbed Oumuamua, it was riding a hyperbolic trajectory, diving in from deep space. The trajectory was unusual, but its physical behavior was baffling. As it headed away from the sun, the object accelerated, pushing back against the sun's gravitational pull without displaying the visible dust and gas tail that acts as a thruster for typical comets. Traveling at 87 kilometers per second, it was moving far too fast to be caught. By the time astronomers established its orbit and realized what they were looking at, it was already leaving, taking any chance for close-up observation with it. This data vacuum forced the scientific community to question the physical laws governing space debris as they struggled to explain how a solid object could propel itself without a visible exhaust. Harvard professor Avi Loeb looked at the limited data and proposed an artificial origin. Loeb calculated that the only way to achieve that specific rate of acceleration without visible outgassing was if the object was incredibly thin, less than a millimeter thick. Because a naturally formed object of that shape was highly improbable, he argued it was an alien light sail pushed by solar winds. This hypothesis met resistance from the wider academic community. Researchers Darryl Seligman and Jennifer Bergner countered with a natural explanation. Oumuamua was a dark comet. Their model suggests that water ice bombarded by cosmic radiation in deep space can trap pockets of invisible hydrogen. When the object nears a star, the heat reorganizes the ice, releasing the hydrogen into the vacuum. This acts as a hidden thruster, providing its acceleration without releasing any visible dust. Validating this theory required a search through the data of our own solar system, looking for local asteroids that displayed that same non-gravitational behavior. When scientists ran the numbers on objects orbiting near Earth, they found 6 asteroids, including 1,998 KY26, exhibiting the exact same acceleration as Oumuamua, despite having no visible coma. These local findings prove the dark comet mechanism operates as a natural physical process. The discovery offered a grounded explanation for Oumuamua's function, reducing the necessity of the artificial light sail hypothesis. In 2019, a second interstellar visitor arrived, designated 2I Borisov. This object behaved in a manner that radically differed from the first. Borisov acted like a standard comet. As it approached the sun, it ejected a massive, highly visible tail of dust and gas that stretched 140,000 kilometers into space. Spectral analysis of that tail revealed unusually high levels of carbon monoxide. Because carbon monoxide requires extreme cold to freeze, its abundance indicated Borisov likely formed far away from a warm star, perhaps in the frigid environment of a red dwarf system. Borisov proved that not all interstellar visitors are anomalous. Some are traditional comets, highlighting the need for a larger, more diverse sample size to understand the variety of objects traveling between stars. In July of 2024, the Atlas Telescope Network, which scans the bright, mass-heavy regions of the galactic plane, spotted the third confirmed visitor, 3I Atlas. This object followed a nearly vertical path. While a circular orbit has an eccentricity of 0, 3I Atlas carries an extreme eccentricity rating of 6, plunging toward the Sun from deep space. Following this steep curve, the object swoops just inside the orbit of Mars before the Sun's gravity slingshots it back out into the void. It is significantly larger and faster than its predecessors. Measuring an estimated 10 kilometers across, 3I Atlas is barreling through our system at 58 kilometers per second. Despite its scale, its brightness barely fluctuates, showing a flat 29-hour light curve. It emits a faint, visible coma and reflects a reddish hue similar to the D-type asteroids found in our outer solar system. These 3 visitors, each displaying distinct sizes, speeds, and chemical behaviors, prove that the galaxy contains a wide spectrum of debris. The scientific goal has now shifted from passive observation to active interception. Catching an object moving at 58 kilometers per second is a severe engineering challenge. No existing chemical rocket has the power to achieve that velocity from a standing launch. Project Lyra proposed bypassing standard engines and relying on orbital mechanics using planetary gravity assists to generate the necessary speed. Their trajectory is counterintuitive. A probe first launches outward toward Jupiter. As it loops around the gas giant, the maneuver bleeds off the craft's momentum, dropping it backward toward the inner solar system. This sets up a solar obirth maneuver. The probe falls directly toward the Sun, utilizing our star's gravity to reach maximum kinetic velocity before finally firing its main engines. This combination of gravitational freefall and engine thrust slingshots the probe out of the solar system at over 70 kilometers per second, fast enough to chase down an interstellar object. While the math is sound, the fuel requirements and the complexity of flying so close to the Sun make this difficult to succeed. Researchers need months of advance notice before a visitor arrives. That early warning system is currently under development. The Vera C. Rubin telescope in Chile is engineered to detect high-speed faint anomalies like these. By capturing millions of images for a continuous, decade-long survey, it will be able to spot incoming interlopers up to 3 months before they reach the inner solar system. The European Space Agency is also building a proactive solution with the Comet Interceptor mission scheduled to launch in 2029. This mission involves parking a fully assembled interceptor probe in deep space. It will wait in a stable orbit for up to 3 years, ready to meet the next interstellar object that crosses our path. The integration of advanced early warning telescopes with prepositioned probes allows for direct physical study rather than remote observation. When the next fragment of another star system enters our neighborhood, the infrastructure is in place to meet it.